Hello students, welcome to Lab Elec05, the RLC circuit. This is part of a fundamental lab offered by the Department of Physics and Material Science in Chiang Mai University. So today we're going to be working with the RLC circuit. The RLC circuit is when you connect the resistor with the inductor and also the capacitor all together, and you tune it with the you supply it with the alternating current voltage. So with the alternating current voltage, you're going to be giving the circuit a frequency, and the resistance of this guy would not depend on the frequency because, you know, a resistance of the resistor is just resistance. However, for the inductor, there's going to be some magnetic flux going on here, and for the capacitor, there's going to be charging and discharging phenomenon going on. Therefore, this causes the phase lag between the voltage and the current, and it gives what you call the reactance, which is equivalent of the resistance, but it does not take away any energy. Where for the inducting coil, you would actually have the reactance to be 2 pi f multiplied by L, and where L is the inductance of the inductor, and for the capacitor you would have what you call the XC, the reactance of the capacitor, which is 1 divided by 2 pi f times C. So as you can see, by tuning the frequency, you can change the XL and XC, and this phase lag would cause VL to be 90 degree ahead of the current and the voltage across R, and VC to be a 90 degree behind the current and voltage across this R. So if you make a plot of this phase of the current and voltage that goes through different part of the equipment, you can create what you call a phasor diagram, where you can put VL on the positive y-axis and VC on the negative y-axis. So from there, you could actually do the calculation using the vectoral, basic calculation by adding VR, which is on the x-axis, and the subtraction of VL minus VC on the plus y-axis, and then you add them in a vector way, and you get the total vector V, which is the total voltage that you supply. So from this phasor diagram, you would actually deduct that, as you know, that whenever we have this kind of circuit, the only part that actually drains the energy from the system is called R, right? The resistor is going to be what would take away the energy. So when you calculate the power, then usually in DC circuit you would calculate power equals IV, right? But from there, that doesn't quite make sense because V is not quite in phase with I, so you need to project V into VR. So V is going to be V cos phi multiplied by I. So again, to calculate VL and VC, VL and VC would be proportional to XL and XC. So you just multiply I with XL, I with XC. So these V are actually measurable, but they don't take away any energy. But you can measure VL and VC by applying the AC voltmeter across this part or this part, and measure VL and VC, and you can create the phasor diagram to calculate what is the phi here. So from there, by projecting V to be V cosine phi, then you can actually calculate the power to be IV cosine phi. And the part cosine phi is what you call the power factor, and it determines how much power is being used in the entire system into the resistor, or how much power is being really put to work. So resonant frequency, as I mentioned, you can tune the voltage VL and VC by tuning XL and XC. So changing frequency here would tune how much VL and VC would be. So if you reach a point where VL and VC are the same, then this y-axis would go to 0, meaning all voltage would go to VR, meaning this angle goes to 0. So this means that you get the maximum voltage on R when VL minus VC equals 0. So then when XL and XC are the same, then you could actually calculate what is the frequency that gives you that number. So by equating these two numbers, then you would get the relation that F resonance is 2 pi divided by square root LC. So this is only dependent to L and C based on your setup. So another thing you could do is previously we connect RLC on the series circuit, but theoretically you could also connect them in parallel circuit. And in parallel circuit, you know that the current would be splitted, and however the voltage would be the same across the entire circuit. So the phasor diagram would look a little different when V and I would actually be the role would be reversed when you talk about like the phasor diagram. However, we will not dwell ourselves into this, but we'll look into another circuit when you connect R in series with L and C, and here with these two coupled together, then when you calculate the impedance, which is the total resistance equivalent of the circuit in the AC, you can actually calculate the impedance Z as R squared plus this relationship with reactance. And if you note, you can see that if you tune XL to be the same as XC, then this term becomes 0. So something over 0 becomes extremely large number. So that means that the L and the C part would take away most of the energy, leaving nothing to R, meaning you have what you call the anti-resonance. And again, you would get the exact same number by using the same L and C. So the frequency for anti-resonance would be 2 pi divided by square root L and C. So there you could actually have the circuit where if you tune it to the anti-resonant frequency, most or no power at all would go into R, but most, if not all, power would go into L and C. So R would get no energy in this case. Alright, so this is our setup. This is our inducting coil, our capacitor, and also our resistor. What you need to do is you need to connect it to a power supply in series. So you know, the voltage goes in here, comes out here, come out here, go in here, comes out here, go in here, and then alternate. So it doesn't matter which way you plug it in, because in alternating current the voltage would actually be switching back and forth. Then put the setup into 1000 Hertz and 5 volt setting, and wire the whole thing in series like this. And from there you measure the voltage across different part of the circuit and make a note and see if the total voltage comes out to be 5, exactly as you expected. And on second part, measure the voltage across R only this time. So then you start with the same setup as previous, and then you change the frequency to plot voltage of R versus the frequency. And we know from previous discussion that from this you would actually have like the maximum voltage across R when you reach the resonant frequency, and from there you can use the resonant frequency to calculate whether or not this is correct L and C that you're reading from here. Alright, so on the third part you do the same thing, but instead you connect the modified parallel circuit. So you connect R to the L and C that are connected in parallel to one another. Then plot VR versus frequency again, but this time you're gonna get a reverse relation where VR is minimized when the frequency reaches the anti-resonant frequency. So, but still, you can still use the same relation, just the voltage across R is gonna drop when it reaches the anti-resonant frequency. Alright, last part, you're going to be working on the fluorescent lamp and ballast circuit. So on the fluorescent lamp, so usually you're going to need a starter and a ballast to keep the fluorescent lamp going. So today we're going to be using what we know from the phasor diagram to connect the entire circuit and then connect the ballast circuit itself. So the entire circuit would be comprised of the total the lamp, which is the part that's actually shining light, which is denoted as capitalized R, and then you would have a ballast that keep the whole thing going, which is the inductor connected with a small r. So so first connect the whole circuit like this, and then you measure the total voltage and measure the V across just this part. So as you can see that if you connect the entire circuit like this, you would actually have the phasor diagram on the bottom left, where the total voltage that's being applied, which is 220 volts across the circuit. If you connect the voltmeter across this fluorescent lamp, then you would actually be able to find what is the VR. However, what's unknown is VL, which is V across the inductor, which is on the ballast side, and also the resistor on the ballast side. So you need to disconnect the circuit and then connect the power supply onto just these two parts. So connect only just the ballast circuit, then you would have this phasor diagram on the right. So notice that the big VR is going to be gone, and also the total voltage that goes across here is going to be what you call the V ballast. So measure the V ballast here, and using the voltmeter, and then you can actually decompose this circuit by calculating VR, uncapitalized R, by multiplying the current that you read from the meter with the resistance value that's written on the board for the ballast. So now that you know the total V on the ballast, and you know that what VR is, you can actually calculate what is the V across this L by using the phasor diagram from here. So you can actually use the vector subtraction, so you know that this is a total vector. So this guy square plus this guy square should be this guy square. So do the subtraction, then you could get VL. So once you know VL, then you can actually calculate the power factor by either from VL or VR, or both of the VR. So either way, and then you can calculate the power factor and calculate the actual power that goes into the circuit. All right, so I think this is all for now, and please enjoy the lab. Thank you.